We are connecting limits, summation notation, and integrals all together. So it's a lot of different stuff. Let's look at these 4 graphs here first. Okay, we're finding the area under the curve. Looking at this first graph, we have drawn this thing and split it up into 2 rectangles to estimate the area under the curve. Right now, is that a great representation of the area under the curve? No, it's fine. Fine at best. Okay, if I broke that up into 5 rectangles, like this guy next to it, is that better? Yeah. What happened to the width of each rectangle? It got smaller. Okay, makes sense. What about 10 rectangles? Is that better than 5? Yeah. 100? Is that better than 10? Yeah, you can see that you're getting almost really close to it, but what's better than 100? How many rectangles would be the best? Infinite amount of rectangles would be the best. If we could split this up so that the rectangles are so tiny that they're almost just straight lines, then you'll get the actual area under the curve, and that's what we're trying to do here. So that's the main idea. All right, so we're going to use this summation notation. So it's been a minute since we've done it, but remember how this works. There's a number on bottom. In this case, I equals 1. I is going to represent which rectangle we have. All right, so maybe this is rectangle 1, 2, 3, 4, 5, whatever. Okay, so we're going to start at rectangle 1. We're going to find the area of that rectangle. And then we're going to find rectangle of area 2, or the area of the second rectangle, the area of the third rectangle, the fourth rectangle, and so on. And then because we've got this summation sign right here, we're going to add them all together until this number on top, which is how many rectangles we want, which in this case is infinite. That's what we're doing. Okay? We're thinking about breaking this thing up into as many rectangles as possible, because if I add them all up, it'll get me the total area. Looking at it in a formula form. Okay? Here's my formula form of this concept. Okay, this is going to be the same thing as from a to b, f of x dx. This right here that I just wrote is going to be the same thing as this summation notation. We're going to find the limit as the number of rectangles approaches infinity. We're going to have infinite amount of rectangles. We're going to start with rectangle number 1, and we're going to keep going until n rectangles. And then right here is going to represent the area of each rectangle. Well, how do you find the area of a rectangle? Base times height, length times width, whatever you want to call it. Okay? And so we need to come up with that for each rectangle. So the first thing here, this delta x, is going to represent the width, how wide each rectangle is. So here's how wide each rectangle is going to be. It's the span of your bounds. So from B minus A, your upper bound minus your lower bound. So in this case, it's from here to here. That's how wide it's going to be. And then each rectangle is going to be divided by however many rectangles you have. So I'm taking this space right here and splitting up into however many parts. So in this case, I'm splitting up by 100. Okay, maybe on this one, I'm only splitting up by 2. But on this one, we're splitting up by an infinite amount. So that's my width. Then I want to find the height of each rectangle. Okay, so for this rectangle right here, how tall is that thing? Well, to figure out how tall it is, you want to know what this x value is right here, and you're going to plug it into whatever this equation is, because that will tell you the y value. That will tell me the height and the width. All right, so to find the height, we are going to take this. We're going to start at my lower bound, and we're going to add to that the width of my rectangle times whichever rectangle it is. So if it's the first rectangle, it'll just be the width 1 time. If it were the 5th rectangle, it'd be the width 5 times. We take that number, we plug it into f of x, we plug it into our original function, and that will be a representation of the height times the width. Is that a perfect understanding of it? No. You're still looking at me like I'm an idiot, but that's okay. That's the concept. That's what we're going to do here. All right, so let's look at it. Let's look at it down here and see what it looks like with a representation. So let's say I had the integral from pi to 2 pi of cosine of x dx. I'm trying to find the area under the curve. So I want to do height and width. How far does my integral span from when to when? Pi to 2 pi. So how much distance is there between pi and 2 pi? Pi. Okay, so this right here represents the width. we take our upper bound minus my lower bound. So we're going to take 2 pi minus pi, and that's going to tell me the width of this thing, which is pi. And I'm going to divide it by n rectangles. So I'm going to divide it by infinity, but it doesn't really matter what that number is. Okay, think about what that is. If it's pi divided by infinity, that's a tiny little baby number that's basically just a straight line. But there's my width, this pi over n concept. Now I need my height. To figure out my height, I need to know the right side of each rectangle. So we're going to use that equation right there. We're starting with A, where A stands for my lower bound. What's my lower bound for this problem? Pi. My lower bound is pi. So right here, I put in pi. Plus my width, which was this guy right here, times I, where I represents whatever rectangle you're looking for. And then let's show you what this means. So again, here's how we set it up. We find the limit as my rectangles approach infinity. We're starting with our first one, we're going to n. This right here is the width, so that pi over n. And that other part right here is the height. This whole thing represents the height. Where we took this pi plus pi I over n, we took this thing right here. Oh, that's an awful color choice there. Let's try that again. That right there, we plugged it in to the original function. In this case, the original function was cosine. That's how we do this problem. All right? It is weird. When you do it at first, it's not going to make any sense. Here's the best news about these problems. They're always going to be multiple choice. And if you have just the slightest idea of what's going on, you at worst have a 50-50 guess. Okay? You can probably eliminate 2 answers right from the start and at least narrow it down to 2 and guess from there, and chances are you'll be pretty good at this. Questions so far? That's my answer. That is me starting as an integral and writing it in summation notation. Okay? And so let's look at how these look. So this is a very good example of what it would be like on the test. You start with summation, you're trying to go to a limit. Or start with the integral, you try to go to a limit. So we're going to do 2 things. We're going to find the width. We're going to find the height. If we can identify those 2 things, we'll do well. So we're starting off with a width. Show me with your fingers, how far is your integral going to span? Good job with the fingers. It's 3. Okay? 3, because I'm going from 5 to 2. 5 minus 2. Oh yeah, that's 3. And I need to divide that by however many rectangles we have, which in this case is 3n. So this is my width. So looking at my multiple choice answers, which one can I eliminate right now? A and C, because A, it says 1 over n. That's not my width. C, it says 1 over n. That's not my width. It's 3 over n. So it's either B or D. Then we're going to find the height. To find the height, we are taking my function, which in this case is x squared, and we're going to start with my lower bound and add my width. So what's my lower bound going to be here? 2. We're starting with 2, and we're going to add my width, which is 3 over n times whatever rectangle we have. And in this case, they're using the letter k instead of I. That's fine. 3kn. So which choice is it here if that's my width and that's my height? B or D? D, because I want that 3 in front of my k, because my width was 3. Kind of makes sense on how that works. The limit part is always going to be the same, correct? This first chunk is always going to be the limit as n approaches infinity. K is going to be equal to 1, or I, and n is going to be on top. You never have to do that. Again, it's going to be matching. It won't be that bad. The one on the bottom of these notes is the hardest one. Let's flip to the back side and do the top one next. Work with your neighbor, figure it out. For the most part, we did well on this. Let's look at it together. We're talking width and height, so let's start off by finding width. Kevin, how far am I spanning on this one? 3, because he's going from 0 to 3, so you need 3, and then what do you got to do with that 3? Put it over n. That's the width of each rectangle. Okay, that's this part right here. So which ones could you eliminate just from that, Kevin? A and D. A's got a 2 on top. We don't want that. D has a 1 on top. We don't want that. So we've already got it down to 50-50. Just by understanding that, hey, the bounds are 3 apart, I've got it to that point. Then we're doing height. Our function is e to the x, and up there I'm doing upper bound plus the width. I'm sorry, lower bound plus the width. So, Simon, what's that going to start off with? It's going to start off with 0 plus 3 over n, and in this case, my rectangle is represented by the letter I, so 3 over n times I. So what is the right answer here, B or C? It's C, because there's a 3 there, and that one's got a 2. Again, the matching part's easy. It's a weird concept, but you can match. Okay? Try the next one. Raise your hand when you're done. I want to come over and check it. What is the definite integral that matches this limit summation notation? So we're starting with this guy now. We're going opposite of what we've done so far. We're starting with this, and we're writing the integral. There are 2 things we need. We need bounds, and then we need an equation that goes right here. So when you started up on this problem here, Tori, what did you look at first to help you out? Good. This is the 4. That's how wide, or how, you said it even better than I did, how far they are apart. Okay? These 2 numbers are going to be 4 apart, okay, based on the width. Once we've got that, Mackenzie, what did you say next? Mm-hmm. Good. Basing on those 2 things together, she knew she was starting with 3. There are 4 parts of the top number 7. Then the only thing left is the equation, and that one's not too bad. This is the lower bound plus the width, so whatever they are doing with that is going to be the function. In this case, it's just squared. So my equation is x squared for that one. Questions so far? Again, you'll get better. It's weird at first. Try the next one if you haven't already. I'm not giving you any more time. Let's look at this one. Which of the definite integrals is equivalent to this limit? We've got that thing right there. When you start on that problem, Eddie W., what did you start off by looking at? That's okay. So the 4 right there, that's going to be its lower bound. So based off of that, which ones could we eliminate? A and B. So we got 2 of them. We've eliminated A and B. Great. That helped us out quite a bit. What could we do next here? How could we eliminate C and D? Both of them are 4 and 9. So the width is 5. We know that. That doesn't help us at all. What's the thing that's going to differentiate this from being C and D? Amanda?
The actual equation, and because we know that the lower bound is 4, we know that the 4 is there because it's a lower bound, so it's going to be C, not D.
Good. If it were this right here, if it were D, what number would this be instead of 4? It'd be an 8 because you would take the 4 plus 4. But it is a 4, and when I plug it in, I want it to stay a 4. That's why the answer is C. Okay, a little bit more challenging. The last one we got here is the most challenging. Flip back to the front page, look at that bottom one, and figure out what it is. When you got an answer, show it to me. Let's look. This one's a little bit more challenging. So far, we've been able to just look at it and get an answer. This one, you might actually have to write something down to help us out. Okay, so if we're doing width here, as I look at this problem, this is going to be my original integral. So, Sarah, what's my width going to look like here? Yep. Good. Yeah, 3 over n here for the width itself. So the width is 3 over n. So based off of that alone, we can at least eliminate C. So even if that's the only thing you can do, you can at least eliminate one choice. You got a better chance of guessing here. All right, so we got that. Then we're doing height. And to me, the key to this is thinking, what was my original function? Well, my original function was 1 plus 4x. And I'm going to plug in my x value for x. To get that x value, I need my lower bound plus my width. So what's my lower bound starting with here? We're starting with 1. And then we're adding to that 3 over n with the letter I here. So I got that right there. Then what do I need to do? That choice isn't over there. What could I do from there? Distribute. And then combine. We get 5 plus 12i over n, all square rooted. 5 plus 12in, all square rooted. That's where I'm getting letter A from. A little bit more challenging, But that one right there is harder than any I've ever seen on a practice test. So if you can do that one, you can do them all. Okay, just the little weird step of distributing.